Welcome to exercise 3 of chapter 9. The goal of this exercise is to explore the QR decomposition of matrices that are either already orthogonal or sort of kind of mostly orthogonal, but not fully orthogonal, and so on. There are 3 parts to this exercise, and I'm going to swap back and forth between talking about the exercise instructions in this book PDF and Python. So for each part, I'll switch back and forth. Okay, so the first part is pretty straightforward. We want to create a orthogonal matrix from a 6 by 6 random numbers matrix. So basically, we just want a 6 by 6 orthogonal matrix. And we're going to call that U just to differentiate it from Q. Okay, so U is an orthogonal matrix. And then we're going to take the QR decomposition of U. Now that's interesting because the goal of QR decomposition is to orthogonalize a matrix. But what happens if the matrix is already orthogonal? Well, one consequence of that is that the R from QR decomposition will equal the identity matrix. So part 1 of this exercise is to confirm that that is the case. And I will talk about why that is the case when we get there. So here we are in Python. You can see I'm creating an orthogonal matrix from a 6 by 6 random numbers matrix. Now, of course, this matrix here is not orthogonal. I mean, it potentially could be, but the probability of getting an orthogonal matrix at random for a 6 by 6 matrix is so astronomically unlikely. Anyway, we don't need to talk about it. Okay, so I take the QR decomposition of a 6 by 6 random numbers matrix, and here we don't need R. We're going to compute a separate R later. So I just get out the Q, the orthogonal matrix, which here I'm calling U, just to differentiate it from Q. Okay, here this code is commented out. I'm going to use this for parts 2 and 3 of this exercise. Okay, so now this might seem a little bit confusing because I'm computing the QR decomposition twice, but here, I don't actually care about the QR decomposition per se. I just want an orthogonal matrix. And one way to get an orthogonal matrix is by QR decomposition. Later in the book, you will learn that you can also get an orthogonal matrix from random numbers by taking the eigendecomposition or the singular value decomposition of a symmetric matrix. So that is a different way to get an orthogonal matrix. So here I don't really care about QR per se. I just care about getting an orthogonal matrix, and that's what I do here. Okay, now I really do care about QR decomposition because now I want this matrix R. I want to see what R is going to be, given that we're taking a QR decomposition of a matrix that is already orthogonal. Okay, so here I'm printing out R. Okay, so run all this code. And we can see that R is actually the identity matrix. It's the 6 by 6 identity matrix. Now the question is, why does that happen? And the answer, which I hope you have taken the time to think about before listening to me explain it, the answer is that, remember, you can think of R as being like the residual. It's what's left of the matrix after you orthogonalize each column relative to all the previous columns. Now here's the thing. All of the previous columns in U are already orthogonal. So each column is already orthogonal to all the other columns, which means it's orthogonal to the previous columns, which means that there is no residual. So R just ends up being Q. So, if you want to write out the QR decomposition, well, Q is already an orthogonal matrix. And so R is just whatever matrix multiplies Q to give us U, which is the identity matrix. Okay, so that is why R is necessarily the identity matrix. I'm rounding here because there's just going to be some computer rounding errors. We can have a look at that if you want. So you can see from tiny, look at this, 10 to the minus 16, 10 to the minus 17, and so on. Okay, so that is part 1 of this exercise. Remember that there are 2 properties of an orthogonal matrix. One property is that all of the columns are orthogonal to each other. So the dot product of every column with every other column not equal to itself is 0. That's one property. The second property of a Q matrix or an orthogonal matrix is that the norms of all the columns is 1. So the dot product of every column with itself is 1. So the second and the third part of this exercise is basically exploring the impact of changing each of these properties separately. In part 2, here we want to leave all the columns being orthogonal to each other. So all the columns are still pairwise orthogonal, but we are going to change the norms of the columns in this matrix so that they are no longer 1. So what I instruct here is to set the norms of columns 1 through 6. Remember, this is a 6 by 6 orthogonal matrix. So set the norms to be 10 through 15. So column 1 has a norm of 10. Column 2 has a norm of 11. Column 3 has a norm of 13, 12, and so on. And then we take that modulated U matrix. So this is no longer an orthogonal matrix. It still has all pairwise orthogonal columns, but the individual columns no longer have unit magnitude or unit length. Okay, so then apply QR decomposition on that modulated U matrix. And then we want to inspect its R matrix. So I'll switch to Python and show you the answer to that question. And don't worry about this third part. I'm going to come back to that in a few moments. So to implement part 2, here I'm going to uncomment this code that we have here. So modulate the column norms. Essentially what I'm doing is taking each column in U. So I'm not changing this line, right? We still have our random orthogonal 6 by 6 matrix. But now for each column of U, I'm multiplying all of the elements in that column by 10 plus the column index. So this is how we modulate the norm of each column. Okay, and then let's see, we don't worry about this. That's for the next part. Here we do the QR decomposition. And well, we also want to inspect this. But let's start by looking at the R matrix of this QR decomposition. So this is really interesting here. We see that it's not the identity matrix, but instead it is still a diagonal matrix. R is still a diagonal matrix. And that should be not surprising because this matrix U still satisfies one of the properties of an orthogonal matrix, which is that all of the columns are pairwise orthogonal. So R is still diagonal, but the diagonal elements of R are now the norms of each column of U. So that is a pretty neat feature of QR decomposition and the diagonals of R, in particular for when you already start off with a orthogonal matrix. And again, that should make sense because the formula here for QR decomposition is U equals QR. Now, U is already pairwise orthogonal column-wise. So that means Q doesn't really have to do much, right? When you think about the Gram-Schmidt algorithm here, all of these individual columns, these pairwise columns, are all zeros. So the dot product here is 0. So when we loop through all this, we're subtracting nothing. We're subtracting zeros, and then over and over again, keep subtracting zeros. And then here, we are normalizing. So, and where does that norm go to? Well, it goes into the residual matrix, which is the R matrix. So Q has all columns with a unit norm, and that means that all of the norms of each column have to go into the diagonal elements of R. Okay, and then we wanted to print out Q transpose Q here, and then you see that that is still the identity matrix. That shouldn't be surprising, actually. That's the definition of Q. So this is just a confirmation that the columns of Q have unit norm, and the diagonal elements in R have the norms that we created up here. Now, here we are with the third part of this exercise. We want to break the orthogonality of U by setting one element in U to be 0. And here I specify the element in row 1 and column 4. There's no reason why it has to be this particular element. The only reason why I did this was just as a bit of a reminder for the potential for confusion, the risk of confusion that comes when you are translating between math notation and coding notation in Python. So you have to make sure you get the indices correct. Okay, so what happens to R when we break the orthogonality, and why does that happen? So I'm going to re-comment this line for part 2, and then comment out this line. So here you see the indices. So this is index 0, 3, and that corresponds to matrix index 1, 4. Okay, so let's see. Yeah, and then we're going to print out R again. Oh, before I do this, just to mention, this matrix is still mostly orthogonal. It is not a truly orthogonal matrix because not all of the columns are orthogonal to each other, but it's pretty close, right? Except for one element, this matrix is orthogonal. So it's almost an orthogonal matrix. Okay, so now what happens is R looks almost like the identity matrix, except all of the elements, or the elements in the upward diagonal in the fourth column and the fourth row are now non-zero, right? So this corresponds to column index 3, which is here. So it's the fourth column with index 3. And you can see that in the upward diagonal, these elements are no longer zeros like they are for every other column. And the reason is that for all these other columns, they are already orthogonal to all the other columns in the matrix. The only column that is non-orthogonal, that starts off being non-orthogonal in U, is the fourth column, and so R needs to absorb the residual that we projected out of Q, right? So again, let me just go back up to this Gram-Schmidt algorithm here. So for all of the columns, this value here is 0, which means we're subtracting off nothing, except for all of the columns that involve column 4. So are all the dot products that involve column 4, because then we change this. So now this is going to be small because it's mostly orthogonal, but not exactly 0. So then for column 4, we actually are going to be modulating Q. So this was a relatively long exercise for this book, but I hope you enjoyed working through it, and I hope you feel like you have a better understanding of QR decomposition and the interpretation of Q and of R.